Hi guys, in the last lecture we started with the stability of a power system. We first saw what is meant by stability and what are the various kind of stabilities defined for a power system. We saw three kind of stability. One was the voltage stability, in which the voltage must lie within plus minus 5% of the rated value. Then frequency stability, in which the frequency must lie between plus minus 1% of the rated frequency. And then the angular stability, in which we define three types of stability: steady state stability, transient stability, and the dynamic stability. Then we talked about synchronous machine. In this we saw the first of all inertia constant. So we defined two inertia constants, m and h. M was defined such that half omega m omega s is equal to energy stored and gh is equal to energy stored. Okay, here E refers to the kinetic energy of the system. So M had the unit megajoule second per electrical radian. H has the unit megajoule per MVA. And M can also be written as GH by pi F or GH by 180 F. Okay. Pi or 180 will depend whether you are finding M in megajoule second per electrical radian or megajoule second per electrical degree. Then we saw swing equation. This was m d square delta by dt square is equal to Pm minus Pe, where Pm is the mechanical input, P is the electrical output in megawatt, or H by pi F d square delta by dt square Pm minus Pe, but here powers were in Pu. Then we saw how we can convert our two machine system into a single machine system. If machines are swinging coherently, M was equal to M1 plus M2. If they were swinging incoherently, M was equal to M1 M2 by M1 plus M2. Okay. So this was the methods that we studied in the last lecture. In this lecture, we will focus our attention to the steady state stability. So first, let us understand what is meant by steady state stability. Steady state stability refers to the system's ability to regain synchronism after it experiences a small disturbance. Okay. So it refers to synchronism after a small disturbance. So remember, in steady state stability we will only talk about small disturbances. So in any problem, if there is given a small disturbance, you have to understand that problem is related to steady state stability. Now here we will represent the generator as constant EMF source with a reactance J-axis. Okay, or we can say generator is modeled as a constant voltage source behind subtransient reactance, and that constant voltage is actually the induced EMF of the generator. Now electrical power of a generator is given as mod V mod E by X sin delta, or we can say P max sin delta. Okay. Now what happens is that steady state will be when speed of the machine is constant. That is, the rotor of the generator rotates at a constant speed. That means acceleration must be 0. If acceleration is 0 from swing equation, I can say Pm is equal to Pe. Okay, because Pm minus Pe must be 0. Pm minus Pe is also called as Pa, which is your accelerating power. Okay. So there must be no accelerating power to reduce the acceleration to 0 and make the speed constant. Now suppose initially the machine was operating in steady state. Before the application of a small disturbance, the machine is operating in steady state. Then Pm will be equal to Pe naught. Let us say, which is equal to P max sine delta naught. So from here I can calculate delta naught, which is sine inverse Pm by P max. So this is the initial operating angle of the rotor. Now suppose I change delta naught to delta, where delta is delta naught plus delta delta. Then what will happen to Pe? It will become P max sine delta naught plus delta delta, which will be P max sine delta naught cos delta delta cos delta naught sine delta delta. Now since delta delta will be small, we are talking about small disturbance. Sine of delta delta can be replaced by delta delta and cos of delta delta can be taken as 1. So it will become Pe is equal to P max sine delta naught, okay, plus P max cos delta naught into delta delta. Now this is actually Pe0 plus this is del Pe by del delta at delta naught into delta delta. Del Pe by del delta is also called as synchronizing power coefficient for a synchronous machine. Now suppose we apply swing equation md square delta by dt square is equal to Pm minus Pe. This will be equal to Pm minus Pe naught minus del Pe by del delta into delta delta. Now del P by del delta will be taken as delta naught. We know that Pm is equal to Pe naught, so this will get cancelled out. So here I have assumed that the mechanical input remains constant equal to Pe naught. Delta is also equal to delta naught plus delta delta. Hence, del square delta by del t square will be del square delta delta by del t square. So this equation will become delta delta by delta t square plus del P by del delta at delta naught into delta delta. To determine the characteristic roots, first we have to determine characteristic equation. So what we will do is del by del t will be taken as d, del square by del t square will be taken as d square. So it will be m t square plus del P by del delta delta naught into delta delta must be 0. So the roots of this equation will be d is equal to minus plus minus under root minus del P by del delta delta is equal to delta naught by m. Now there can be various cases for the roots of this equation, that the roots are real or the roots are imaginary. Now suppose we talk about the first case, in which del p by del delta at delta is equal to delta naught is less than 0. Then the roots which are equal to this, the inner part, that is minus of del p by del delta, will be greater than 0 because del p by del delta is less than 0. So roots will come out to be real. Let us say that d comes out to be plus minus m. Then delta delta will be c1 e raised power mt, c2 e raised power minus mt. So with respect to time, how delta delta will vary? It will vary like this. It will increase exponentially. So that is why this system will be unstable. Why? Because if we introduce a small disturbance, then the rotor angle will keep on increasing. There are no oscillations and there is no boundation. It will continuously increase from a 0 value to a very high value. So this is the case of an unstable system. Let us take another case. If del p by del delta will be greater than 0, then the roots which are equal to d is equal to plus minus del p by del delta at delta naught by m. Since del p by del delta is greater than 0, these roots will be imaginary. Let us say d is equal to plus minus j omega. Okay. So here then delta delta will be written as c1 cos omega t plus c2 sin omega t. Now here, since cos and sin terms are coming, that indicates that the response of the system is oscillatory. So how it will be? Like this. So here we have oscillations which are bounded. Since it is bounded, system is stable. Also, we are neglecting any sort of damping here. If damping were considered, then the nature of the graph will be like this. Delta delta will finally go to 0, so that system settles down to its initial position. Okay. So the oscillations will be damped out. So that system will be termed as stable. Now here the frequency of oscillation is given by omega, which is equal to under root minus del p by del delta at delta naught by m. Okay. This formula can also be written in terms of h. Then how it will be? Minus del p by del delta, m can be replaced by gh by pi f. Now if g is coming, we can replace it like this. Del p by del delta, but in pu upon h. Okay. Earlier del p by del delta will have the unit megawatt per radian, but now we are expressing in pu after dividing it by g. So this will give the frequency of oscillations when a small disturbance is applied to the system. Okay. And we have seen that the system will be only stable if your del p by del delta is greater than 0. So what will my stability criteria will become? If del P by del delta is greater than 0, system is stable. Del P by del delta is less than 0, system is unstable. If del P by del delta will be equal to 0, system will be marginally stable. I use these concepts in transmission and distribution also, but they are derived here like this. Now we know del P by del delta is actually P max cos delta. If it is greater than 0, then delta belongs to 0 to 90 degree. Okay. If it is unstable, delta belongs to 90 to 180. If it is marginally stable, delta is equal to 90 degree, where power will be equal to P max. Okay. So here the system is marginally stable, hence P max is also called as steady state stability limit. Because if you try to draw power more than P max, then system will become unstable or it will lose synchronism. If we understand this by in terms of power angle curve, so this region is stable and rest of the region is unstable, and delta is equal to 90 is marginally stable, or that is the limit of the stability. Okay, this fact was directly used in synchronous generators also, that the region from 0 to 90 is the stable region for synchronous machine operation. Now how to improve steady state stability? First of all, what is meant by improving the steady state stability? It means we have to increase steady state stability limit or Pmax. If you increase Pmax, it will be termed as improving the stability, because the system will be unstable if power exceeds Pmax. If Pmax itself is very high, then the chances of unstable operation are very low. So you have to increase Pmax in order to improve the stability of the system. Now how to increase Pmax? Pmax is actually mod E mod V by Xs. So the first method will be to increase mod E, which is done by operating the machine under overexcited condition. Okay, high excitation EMF implies that the machine is running at overexcited condition. We cannot change terminal voltage because it depends on the voltage of the bus bar or the infinite bus bar or the grid, so that it remains constant. We can reduce transfer reactance or we can reduce synchronous reactance. How to reduce synchronous reactance? We can use series compensation. If you use series capacitor, that reduces the reactance and increases the Pmax. By using double circuit line, in case of double circuit line, equivalent inductance will be L by 2, as two lines will be connected in parallel, hence the reactance reduces. By using bundled conductor, what happened in bundled conductor? The GMR is replaced by self GMD. So self GMD is more than GMR, hence inductance reduces. Otherwise, we can also use parallel line system, that is when multiple transmission lines are connected in parallel. And the last method is called as SVC, which is your static VAR compensator at midpoint of the line. Why we only choose midpoint? Because what happens, the actual voltage profile of a transmission line is like this. The maximum voltage fluctuation occurs at the midpoint. Since maximum voltage fluctuation happens at the midpoint, we have to place the compensator at midpoint. Okay. So usually sending and the receiving end voltages are same, but midpoint has the maximum voltage fluctuation. So now let us understand how SVC can help improve the stability. So this is how I have divided the transmission line into two sections, JX and JX. I am assuming that the sending end and the receiving end voltage have the same magnitude, and I am placing the compensator at the midpoint. Now here we will assume that SVC is ideal and it only injects reactive power. That is, real power of SVC is 0. So whatever is the real power in the transmission line will remain same, because SVC will neither inject the real power nor it will absorb any real power from the system. It will only deal with the reactive power. Now to solve this system, it is better that first I find the equivalent circuit about the midpoint and then I will connect the SVC. So first let us remove SVC. Okay, we haven't applied SVC. So how will my system look like? This will be E angle delta. This is JX. This is also JX. Here this will be E angle 0. This is my midpoint where the voltage is V. Now since we have disconnected SVC here, or we have opened the load terminals, so directly indirectly we are calculating the Thevenin equivalent about midpoint. Now how to calculate the open circuit voltage at midpoint? First we have to find the current. What will be the current? E angle delta minus E angle 0 by J 2x. Now voltage of the midpoint will be E angle delta minus J x into I. How much will this come out to be? If we multiply I by Jx, voltage will be E angle delta minus E angle delta minus E angle 0 by 2. So it will be E angle delta plus E angle 0 by 2. Now if we simplify this expression, E angle delta plus E angle 0 by 2, then what will happen is E cos delta plus J sin delta plus 1 by 2. Now 1 plus cos delta will be 2 cos square delta by 2 plus J into 2 sin delta by 2 cos delta by 2. So we can take out common 2 cos delta by 2. So it will be E cos delta by 2 cos delta by 2 plus J sin delta by 2. So it will be E cos delta by 2 angle delta by 2. So this will be the midpoint voltage of the transmission line. Now to calculate Thevenin equivalent completely, we need to find the Thevenin impedance. For that we will short circuit all the EMF sources. So what we will do is, we will short circuit these sources. Now if we calculate equivalent reactance, Jx and Jx are in parallel. So X Thevenin will be X by 2. So it comes out to be X by 2. Now we have the Thevenin equivalent, which is V Thevenin, E cos delta by 2 angle delta by 2 and X Thevenin. So what to do now? To solve the system, now we will connect the SVC at the midpoint, or we will connect the SVC to the Thevenin equivalent about the midpoint. So the circuit shown in this figure indicates Once we have the Thevenin equivalent, we have connected the SVC with the Thevenin equivalent. Okay, here V Thevenin is E cos delta by 2 angle delta by 2. X Thevenin is actually x by 2. Now the first condition that we studied was SVC must not exchange any real power, only reactive power must be present in SVC. Now we know the real power when resistance is neglected always flows from a higher angle to the lower angle. Since real power is 0, angles of both the voltage must be same. Hence what we are doing is we are representing SVC by a reactance in series with a EMF source. Reactance is XS, EMF is ES. But ES will also have an angle delta by 2. Because there must be no real power exchange between the midpoint and the SVC. So midpoint voltage as well as the SVC must have the same phase angle. Otherwise power will tend to flow from higher angle to lower angle. So earlier when we did not place SVC, this was the midpoint voltage. Now let us calculate the midpoint voltage after connecting SVC. We will assume a current I. I will be E cos delta by 2 angle delta by 2 minus ES angle delta by 2 J x by 2 plus XS. So if we calculate V midpoint, it will be E cos delta by 2 angle delta by 2 minus J I x by 2. Now since every voltage and every current has the angle delta by 2, that can be taken as common. E cos delta by 2 minus x by 2 by x by 2 plus XS E cos delta by 2 minus ES. So this will be the midpoint voltage. Now to determine the power transfer, since SVC is not consuming any real power, that means the real power in the transmission line will be same. So whether you calculate real power between sending end and midpoint or midpoint to the receiving end, that must be same, because no real power will go into the SVC. So whatever is the real power coming from sending end to midpoint will be the same as real power going from midpoint to the receiving end. So how to calculate power? It will be E into V midpoint. What is the reactance between midpoint and the sending end? It is X. What is the angle? Sending end has an angle delta, midpoint has an angle delta by 2. Okay. So what will be the power? It will be mod E square by X cos delta by 2 sin delta by 2. I am substituting the value of Vm in the expression, minus x by 2 by x by 2 plus XS multiplied by, we will multiply this by E by X sin delta by 2 mod E square by X minus mod E into ES by X. Okay, it will be multiplied by sin delta by 2. Okay, so this will be the power. Now let us make some assumption to compare it with the power without connection of SVC. Let us make an assumption that XS is 0 and ES is equal to E. That is, the midpoint voltage is same as the sending as well as the receiving end voltage. So power will be mod e square by x 2x sine delta, because sine delta by 2 cos delta by 2 can be written as sine delta upon 2. If axis is taken as 0, this factor will become 1 minus e square by 2x sine delta, so this gets cancelled out, plus mod e square by x sine delta by 2. So power will be mod e square by x sine delta by 2. Now when SVC was not connected, then the sending as well as receiving end voltage was equal to E, and the reactance between sending and the receiving end was 2x. So P initial was mod E square by 2x sine delta. So now if you see, Pmax after connecting SVC is equal to 2 times Pmax before connecting SVC. Since Pmax increases by the use of SVC, it means stability improves. So SVC has two benefits. It controls the midpoint voltage as well as it improves stability by increasing Pmax. So if we plot it on a curve, if we draw the power angle curve, initially it will be like this, okay, but when we connect SVC, Pmax will double, but angle will also become half. It will become sine delta by 2. So at delta is equal to 180, delta by 2 will be 90. So it will be like this. It will be continuously increasing with SVC. This is without. Okay, whenever delta will be equal to 180, that will actually correspond to 90 degree when we are talking about the power with SVC used. Because with SVC, power is actually mod E square by x sine delta by 2. Okay, so 180 angle will correspond to the maximum value at 90 degrees. So that is how my stability will be improved by the use of SVC. So let us summarize what we covered in this lecture. We first saw what is the meaning of steady state stability. Then we derived steady state stability using swing equation. We arrived at the criteria del P by del delta must be greater than 0 for stability. Then we derived the frequency of oscillation, which is equal to under root minus del P by del delta divided by M, or it was under root minus pi f del P by del delta. So minus will not be there because it will be converted to J upon H, where this value will be in Pu. This was the frequency of oscillation. Then we saw how to improve steady state stability was by reducing the transfer reactance or by increasing the EMF, in which we saw one of the methods was to use SVC. When we use SVC, power becomes mod E square by x sine delta by 2, where x is equal to transfer reactance by 2, because the reactance between the sending and the receiving end was represented as 2x. So x is actually half of the reactance between the sending and the receiving end. If it is given to you that the reactance from sending to receiving is 0.2 pu, x will be 0.1 pu. It is half of the transmission line reactance. So this is all about your steady state stability. In the next lecture, we will start with our transient stability. In steady state stability, the important thing is to remember the concept of SVC, though you may not remember the derivation, but you have to remember what is the effect of using SVC in the system. And the other thing that you have to remember is the frequency of oscillation whenever we apply a small disturbance. These two things you have to remember for the case of steady state stability.